let me begin by doing a quick reminder of the stuff that we finished with last week. So we introduced this thing, we call it Vn. So Vn, and then you have a total of n vectors. So that's what we have over here. And this is equal to, by definition, this is the way we define this quantity, is I should say that the vectors, that these vectors over here, these are n-dimensional vectors. So these x's that make up these terms, they are in Rn. These are n-dimensional vectors. So we have a total of n vectors, and they're all in Rn. So these are going to be the setup here. And then this is equal to, by definition, this is the oriented volume, that is the oriented volume of the parallelogram. Let me put volume in quotation marks. This is the oriented volume of the parallelogram that is determined by these vectors. Now, I put volume in quotation marks because the subscript here indicates the dimension in the space that we're working with. So V subscript 1 will indicate one dimension. So in one-dimensional space, it's not the volume, it's the length. In two-dimensional space, if this is V subscript 2, then that would denote area. V3 would be the ordinary volume that you're used to. But if you go beyond that, you cannot visualize it anymore, but we still say volume. So we just use the same word volume, but the understanding here is that volume is really a measurement of the dimension of which you're in. Just a quick comment about seeing the exam. You should not click on the exam, you should click on your grade. You should be able to find the option for your grade and then click on the grade, and then you'll be able to see what you got wrong on the exam. And we mentioned some properties. So here are the basic properties of this. This is called the volume, the oriented volume form. So this thing over here, called the oriented volume form. So the first property that we mentioned was that this is called the scalar multiple property. It basically says in words, it says that if a single vector is multiplied by a scalar, then the scalar can be factored out. So if you want to write it mathematically, we're saying that you have a bunch of vectors, and then you have some vector somewhere. It does not matter which coordinate, but let's suppose it's at coordinate, at the ith coordinate, and then you end up multiplying it by some kind of constant, ai. So you multiply it by a, then you can factor out the a. You can factor out that single term a, and then you keep everything exactly as it is the same. So you have x1 up to xn. So this is what we call the scalar multiple property. The other property that we mentioned, this is called the alternating property, which in words it says if you flip two vectors in the oriented volume, you change the sign, because you're changing the orientation of the parallelogram. So mathematically what we're saying is that if you have some vector at the ith position, and then you have another vector somewhere else at the jth position, and you take those two vectors and you interchange them. So you can take these two vectors over here. So you just interchange these two vectors. Then by interchanging those two vectors, you would end up with Vn x1, and now you have xj, and then you have xi. So you're interchanging those two, but you're keeping everything else the same. And when you do that, you have to make sure that you introduce a negative sign. So you're going to say that this is equal to, and there's a negative sign that we pick up when we do that. So this is going to be the negative of what it was before. This is called the alternating property. And as a consequence, so an important consequence of the alternating property is that if you have a repeating vector, then the alternating volume, and the volume is equal to 0. So if one of these vectors somewhere repeats over here, then because by interchanging them you're getting the same thing, you're getting a number is equal to its negative, and the only such number is 0. So that's the alternating property. Now the next property that we mentioned, this one's a bit harder than the other ones, but this is called the distributive property. Distributive property. And the distributive property says that, let's suppose you have Vn of x1, x2, and then somewhere you have xi, and you add to it another vector. You go ahead and you add to it another vector, let's call it y, and you keep everything else the same as it is, and you have xn. So you're only adding an additional vector just to the ith position. Everything else remains the same. Then the distributive property says that it's basically like multiplying these out. That it's going to be equal to Vn of x1, x2, xi, xn, and then plus Vn of x1, x2, and now you have to do the same thing, but this time with y, and then you have up to xn. So the reason why it's called the distributive property is because if you look at this, you're basically putting all of this stuff together first, which is this piece over here, and then you do the same thing, but it's like you distribute. You have two terms over here, and then you distribute. It's almost as if you take all of this now, and now you include it with the y, and you have the same thing, but now instead of using xi, you use just y by itself. So this is called the distributive property. And then the fourth property that we mentioned, the fourth property is what we call so I call this the unit cube, and I put it in quotation marks. I'm going to put cube because this is a general cube. This is not necessarily a three-dimensional cube. This is an n-dimensional cube. A two-dimensional cube is technically called a square. So the unit cube identity would say that if you want to calculate the n-dimensional volume of the unit cube, and the way you get the unit cube is by using the standard basis vectors. The standard basis vectors, when you put them together, they give you a cube. They give you a unit cube which has volume equal to 1. So if you take the standard basis vectors in the order in which they are commonly written, then this is just equal to plus 1. Because the picture is you have a cube of volume equal to 1 unit. So these vectors, they make up a cube. So these are the four properties that we mentioned about how oriented volume works. And by the way, the reason why we're talking about volume and not absolute volume, because usually if you have a parallelogram, you might argue that it makes more sense to talk about the volume as opposed to the oriented volume, because the answer could come out to be a negative number, is because these nice properties, they only work for oriented volume. These are nice properties. So if we try to do this using the absolute volume, it would not work out as nicely. Now, if you want to actually calculate the volume of the parallelogram, if you get a negative number in the end, then you just ignore the minus sign. So if you have three vectors and you want to determine the volume of the parallelogram that is determined by those three vectors, if you do the calculation and it comes out to be like -10, then you know the actual volume has to be 10, whereas the oriented volume is -10. So now let's do some, well, we'll do some examples involving this. We already did an example last class, but we'll do more. But I also, before we do some examples, I want to tell you what the determinant of a matrix is. So now we can give a definition for what a determinant of the matrix is in a way that is not mysterious. Because when you first learn about the determinant of the matrix, it's this really bizarre rules. It's a bunch of bizarre rules of how you multiply out numbers in the matrix to get some kind of quantity in the end. And it's not clear why the rules are the way that they are or what you're even doing. It just comes up in some calculations that you do. But now, because this is a linear algebra class, we'll be able to define what that is. So let A be a square. So here we need it to be a square matrix. So determinants are defined for square matrices. Be a square n by n matrix. Let's actually just write it n by n. Be a square n by n matrix. So here's how the determinant is defined. The determinant of the matrix is equal to, by definition, it's the oriented volume of its columns. So you're going to take the oriented volume of the columns that make up the matrix. So you're going to do the first column, column 1 of the matrix, column 2 of the matrix, column n of the matrix. You're going to take the columns of the matrix, and then you're going to calculate the oriented volume. That's the way you do it. Now, the significance of this number and why we care about it will be explained later on, but you can think of it like this. So you can think of the determinant of the matrix A as the oriented volume of the parallelogram that is determined by its n columns. So the columns of the matrix, they end up determining a parallelogram, and it's the volume that parallelogram takes up. So let's do some examples of where we do this. By the way, I wrote it in columns. It actually works with rows as well, but we'll get to that. When we talk about the properties of the determinant, you'll actually see, you'll get the same answer if you use the column, the rows as well. But let's just keep it as the columns for now. And let's start with an example. I want to do a 3 by 3 matrix example so we get to see how this works. So in this example, our matrix will be the following 3 by 3 matrix. So 1, 0, 2, say -1, 2, 1, and 3, 1, -2, like so. And we're going to find the determinant of the matrix. Well, the way we do it is you have to look, you're going to look at the 3, you see you have 3 columns over here. So these 3 columns, they're vectors. You can think of these, as vectors in R3. They're vectors in space, in 3-dimensional space. Right, this is a vector, that's a vector, this is a vector. And the determinant of this matrix would be the three-dimensional volume that is determined by these three vectors. So you know that sometimes you write a vector like this, as you know. You can write it like that, but I'll just stick to writing them as columns, so it looks just like what we have above. So the first vector is 1, negative 1, 3. That's the first vector. Then the next vector is 0, 2, 1. And the third vector is 2, 1, negative 2. Okay, it's just the volume, which in plain, if you want to say this in plain words, the determinant of this matrix is the oriented volume of the three column vectors of the parallelogram that is formed by these three column vectors. So if you draw the picture of this, we're not going to draw any careful pictures because it's not necessary for us, but you have three vectors over here. So maybe your first vector looks something like this, maybe your second vector looks something like that, and your third vector looks something like that. So you have your three vectors. These are three vectors in space. These are your three vectors over here. And these three vectors, they determine the parallelogram for you. So you're going to have some kind of parallelogram solid that is made out of these vectors. So something like this. So you end up getting some kind of solid that's made out of these vectors. And that's what the determinant is doing. The determinant is calculating the volume of the parallelogram that is formed by these three vectors. Now, the good news is you do not actually have to draw any pictures because the mathematical rules that we have on this board make it possible for you to quickly figure out what the answer is without the need to draw any pictures. So let's see how we would figure this out. So we're going to write everything in terms of the standard basis vectors. So let's write these in terms of the you could say the ijk vectors, but I'll just use the standard basis like this. So let's write everything in terms of the standard basis vectors. So this is going to be equal to, so in terms of the standard basis vectors, this is V3 of, now we're going to write this vector first. So that vector in terms of the standard basis vectors would be 1e1 minus e2 plus 3e3, comma. Now the vector in the middle, this is the vector over here in the middle. We're going to write that one in terms of the standard basis vectors. You notice there is no e1 component, so you would just have 2e2 plus e3. And then the third vector in the volume calculation would be right over here. So we have to write that one in terms of the standard basis vectors. So we would get that this is 2e1 plus e2 minus 2e3. And now what we do is we kind of use all of these properties together at once. So the property that we're going to use a lot is the distributive property. It's almost as if you're multiplying things out. The distributive property says you kind of think of this as some kind of product. So if it helps, it's what it's saying. I mean, if you think of it as multiplying out these three terms, that's basically what you're doing. If that makes things easier for you to see what's going on. So you think of it as multiplying things out. So let's highlight some of the possibilities, some of the combinations that work. Like for example, you can select this term over here, you can select that term over there, and you can select this term over here. And if you do that, let's just write down what you would get if you were to do that. So you would get plus V3, I'm sorry, let me start again. This is equal to v3 of 1e1, comma 2e2, comma 2e1. And now, by the scalar multiple property, every number, every scalar can be factored out. So we have a 2, we have a 2, and we have a 1. So the common factor is going to be 4. So we're going to have, so this is going to be 4 v3 e1 e2 e1. But here's what you immediately notice. You have repetition. You see that you have an e1 over here and you have an e1 over there. Because you have repetition, you immediately know that it's equal to 0. If you have any repetition in these vectors, it will immediately be equal to 0. So it's true, you could multiply these three terms together, but the problem is it just gives you 0. So there's no need for you to do that because that's not going to give you anything. So you can save a lot of work here by ignoring that. It's not like it's wrong, it's just going to be 0. So there's no need to include it. So instead what we will take this one, we can take E2, but then we have to take E3. Then we have to choose this one. So if we do it like that, we would end up getting V3 of 1E1, comma 2E2, comma negative 2E3. So that's one possible combination. Now there's another possible combination. So we put plus because we're using the distributive property. You think of this as a multiplication that distributes over several terms. Now the other way you can do it is you can pick the first term over here. Instead of taking the second term, so let me say it like this. If you pick the first term here and you pick the second term here, there's no need for you to pick the first term. That's just going to give you 0 because you have a repetition. You're not going to pick E2 either because that's going to give you a repetition. You already have an E2 over here. So to avoid a repetition, you have to pick the third one. So if you pick E1, E2, then you're forced to take E3. But the other way to do it is you can take E3 instead. And now if you take E1 and E3, then to avoid a repetition, you're going to pick E2. So you can multiply these three together. And so you would say plus, you would write that this is V3 of 1E1, comma E3, comma E2. That's the other way you can do it. You write it like that. Now we have some other combinations that work. So you could, if you use, so we looked up at all combinations that involve E1. Now let's look at other combinations. You can pick, for example, E2. If you pick E2, you're not going to pick E2 again. That will give you a repetition. But if you pick E2, you can pick E3. And now if you pick E2 and E3, you're now forced to pick E1. And then you would write plus V3 of minus E2, comma E3, comma 2E1. You write it like this, then plus. Let's look at another combination that works. Now another combination that can work is you can pick an E3. You can pick that one. If you pick E3, you're not going to pick E3 again. You have to pick something different. So you pick 2E2, and now you're forced to pick 2E1. So the last term, the last possibility that we can have is V3 of 3E3, comma 2E2, comma 2E1. And this is what we get. So now it's just a matter of factoring out the numbers and putting everything in the correct order. So now we have these four terms. So you have to factor out these constants. So let's go ahead and factor out these constants. So you factor out the constants. Let's see what we have here. we have a 1, a 2, and a -2. So if you factor these out, this is 4 and -2. That's 2 and -2. That's going to give you -4. So the first term is going to be -4 multiplied by V3 of E1, E2, E3. Now let's go to the second term. The second term, well, that's just V3 of E1, E3, E2. The third term, you'll notice we have a factor of -2. So this is V3 of E2, E3, and E1. And then plus, and then finally the last term, we have the factor, we have 3, 2, 2. This is what we have in the last term. We have 3, 2, 2. If you factor out all of those numbers, that will give us 12. So that would be 12 V3 of E3, E2, E1. So now it remains, now the reason why this is good is because everything is now expressed in terms of the standard basis. But you will notice that some of these are out of order. This is in the correct order. This is E1, E2, and E3. This is in the correct order. And what this means is if you look at this property over here, this is the unit cube identity. If you write the standard basis, which represents a unit cube, its volume is equal to 1. But what about the other pieces? Well, the other pieces, they depend in the order in which they're written, because the order in which you write it changes the orientation. So all of these will either be plus or minus 1. So the remaining terms, so let me just make a comment over here. These remaining terms are all either plus 1 or minus 1, depending on its orientation. And you can determine that. You can determine the orientation by using the alternating property. The alternating property says that if you flip two of these, you have a change in orientation. So it's the alternating property here. You have to put them in the correct order by flipping them around. So the easiest one here, let me just answer someone's question. You can go ahead with your question.
I was just making sure to get the coefficient of the whole term, you just multiply the coefficients of each of the inside terms of each of the E1, E2. Yeah. Okay.
Right. It's just like multiplication. I'm not saying it is multiplication. I'm just saying it's similar to multiplication. That's the way you want to think about it. Yeah, just multiply the numbers. This 12 over here, it comes from multiplying these coefficients together. Now, let's start with the easy one. The easy one is this one over here. This one is equal to 1. This is going to be plus 1. That's plus 1 because that's a unit cube. This is a unit cube written in the correct order, E1, E2, and E3. Now, let's look at this one over here and figure out what it is. Let me do a side calculation. I'll do a side calculation over here, so you get the idea of how it works. So you have V3 of E1, E3, E2. This is equal to, now here's what you're going to do. Take the second and third number, well, not number, vector, I should say vector, and flip them around. Then you get negative V3, E1, E2, E3. But now, because it's in the correct order, it's equal to 1. So this will be -1. So that means that this term, this second term, has to be chosen with the -1 sign. That is the volume of the cube, but with reverse orientation. That's going to be -1. Now, we have this one down here. Let's figure that one out. So let me do it over here on the side. So you have V3 of E2, E2, E3, E1. Let's figure out what that is. Yeah, so every time you flip the vectors, you're changing the sign. you have a sign change anytime you do a flip. So sometimes you have to do multiple flips. So let's see what happens here. Here, so we can do this. We can change these two around. There is more than one way to do this, by the way. I'm not saying this is the only way to do it. And if you flip those two, then you get negative V3 of E1, E3, E2. But then if you look at this, it's still not in the right order. The first one is in the correct position, but these two are not in the correct position. So then what you do is you have to flip these two around again. You have to flip these two. And if you flip those two, then you would get another minus sign. So you would get that this is equal to -1 of -1 of V3 of E1, E2, and E3. So you see that here you have to do two flips to get it back to the original order. And because you're doing two flips, you have two negative signs. So that means the correct sign is +1. It's the negative of a negative. If you have an even number of flips, that's going to be a positive. So this is going to be +1. It's going to be +1. And now for this one, let's put it in the correct order. So we have V3 of E3, E2, E1. Here, you only have to flip. The second one is in the correct position, so you only have to flip the first and third one. And if you do that, that will give you negative V3 of E1, E2, E3. And that is equal to -1. So this piece is going to be equal to -1. And with that, you can now solve the problem. You can now say what the determinant of the matrix is equal to. So the final answer is going to be this. The determinant of the matrix is going to be equal to, so now you just copy and paste the numbers. We had a -4. You see, I'm just going to be copying this. -4, this is 1. Then we have plus. This is -1. Then we have -2 and +1. So you just copy those numbers in. And this will give us -4, 1, plus -1, plus -2, and then -12. Okay, this is what happens when we do that. And if you add this up, this is -4, -5, -7. So you end up with -19. So that's going to be your answer. That's going to be the final answer to your problem. And you can check your answer on Mathematica. You will, of course, be allowed to use Mathematica to do calculations, unless, of course, the problem on the exam asks you specifically to do it yourself. Or it could be one of those problems which is like more conceptual, where you have to understand what you're doing. You cannot just put it into a calculator. But if you're just doing a pure computation problem, then the way you would do it, if you have to do this on a calculator, you would have to input this matrix. This is your matrix. It would just input 1, 0, 2. That's the first row. Then you have -1, 2, 1. That's the second row. And then the third row is 3, 1, -2. That's the way you write a matrix for Mathematica. When you copy that, let's just see what the calculation is. And it should be equal to -19. So we tell it to do determinant of that matrix. And you can see there's the answer, -19. It even tells you how to say it in words, -19. It also shows you where -19 is on the number line in case you do not know that. So this is how we do this calculation. Now, if you understand the ideas behind how this computation was done, there's a shortcut way of doing this. So let me just show it to you. There is a shortcut of doing this determinant calculation without the need to write everything in terms of basis vectors. But I mean, in actuality, that is what you are doing, but not writing out each step. So let's look at this example right here. Let's take this matrix. So we have a matrix, and this matrix is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be our matrix. And we want to find the determinant of that matrix. So here's the way we're going to do it. The idea is, the way we've done it before is you have to consider the 3-column vector. So you're going to introduce these 3 columns like this. So this is going to be your first vector over here. That's your second vector, and that's going to be your third vector. Now, what you do next is you have to look at all of the possible multiplications that you can form. So maybe it's better if I just highlight one way you can do it. So one way you can do it is you can select the number 1, 5, and 9. Because you see, if you select the number 1, you cannot select the number 2 again, because you have that repetition in the basis vectors, as we said. You have to pick one of these three numbers will have to be chosen, and will have to be multiplied against one of those numbers. But it has to be a different basis vector. So if you select 1, you cannot select 2 again. Okay, so if you end up selecting 1, you're not going to select any of those 2 numbers. So if you select 1, you have to go to the second column and choose a number, but it cannot be 2. So for example, you can pick 5, but if you pick 1 and 5, you cannot pick 6, because then these 2 are sharing. There's a repetition in the basis vector. So then you have to pick 9. So that's one way to do it. So one possibility that works here is you do 1 times 5 times 9. And then right over here, you're going to put plus or minus 1. And you have to determine the correct sign. And the way you determine the correct sign, we're going to do this afterwards, but I'm just going to put over here, I'm just going to put the numbers 1, 2, 3. So what the numbers 1, 2, 3 represent, it means that I'm choosing the first number in the first column, I'm choosing the second number in the second column, and I'm choosing the third number in the third column. Okay, that's one way you can do it. Now let's look at another combination that works. Another combination is you can take 1. Now you cannot take 2, as we said. You can take 5, but you can take 8. You can choose 8. So you can end up choosing 8. You can choose 8. And then you can choose 6. And then you have no repetition in the basis vectors. And then you would have, when you do that, you would have 1 times 8 times 6. And again, you either have a plus or minus sign. And the way you're going to determine that plus or minus sign is by looking at how you chose them. So you've chosen the first number in the first column, you've chosen the third number in the second column, and you've chosen the second number in the third column. That's what this 1, 3, 2 means. It just represents the positions of how these are being chosen. Now, another way to do it is you do not have to pick the first number. You can pick the second number in the matrix. You can pick the second number in the first column, pick the first number in the second column, and then pick the third number in the last column. And then the way this is going to look like now is you're going to have 4 times 2 times 9. And again, you're going to have plus or minus 1. And the order in the way you're choosing this is you're taking the second one, the first one, and the third one. So that's the way you can do that. Now, another way, another combination that works, let's look at the other combinations, is you can maybe pick the second number, you can pick the third number, and then you're forced to pick the first number. So if you multiply those three, then you get 4 times 8 times 3, and this is going to be plus or minus 1. And the order in which you're choosing this is you're taking the second number, the third number, and the first number. Again, the 2, 3, 1, it means you're taking the second number in this column, you're taking the third number in this column, and then you're taking the first number in that column. Let's do, there's a few more. There's 2 more that we can do here. You can choose, another thing you can do is you can choose the third one, the first one, and the second one. It's another combination that works. So this would be 7 times 2 times 6. And then again, you have a plus or minus sign. And then the way this goes, this will be 3, 1, 2. And finally, the very last combination that works here is, the very last combination is this, that this would be the very last combination. So very final combination would be 7 times 5 times 3 plus or minus, and this time it's going to be 3, 2, 1. Okay, and now that you've written it out like this, you can now determine the correct lines. So let's start with this one. This one, because it's in the correct order, 1, 2, 3, 1, 2, 3, it's in the right order, we know that this is going to be a positive sign. So this is going to be a positive sign. Now let's look at this one. You see, this is 1, 3, 2. You have to put it in the correct order. In order to put it in the correct order, you have to flip the second and third vector. So now it's in the correct order, 1, 2, 3. But because you're doing the flip, this is now minus 1. Now, if you look at this one, it's 2, 1, 3. So to put it in the correct order, you have to swap these two. So here you have to swap those two. So you would have 1, 2, 3. And this would be also negative 1. Now let's look at 2, 3, 1. 2, 3, 1. This is not in the correct order, but you can swap 1 and 2. So if you swap 1 and 2, that would be 1, 3, 2. It's still not in the correct order, so you have to swap again. You have to swap the second and third one, so that's 1, 2, 3. So now it's in the correct order. But because you're doing 2 swaps, that's 2 negative signs, so this is going to be positive. So that's going to be a positive sign. So this is positive, like that. Now this one, 3, 1, 2. So let's see what we have to do here. So here we have to, if we swap 1 and 3, we have 1, 3, 2. And if we swap those two, we get 1, 2, 3. So here we also get a positive sign. And finally, on the last one, 3, 2, 1, if you swap the first and last one, that will give us 1, 2, 3. So this is going to be a minus 1, like so. And you add those numbers up. So add those numbers up and you get your answer. So now just add those sign numbers up. And if you do that, I'm not going to do that because it's just a matter of multiplying and adding numbers. If you do that, the answer comes out to be 0. The answer comes out to be 0. The determinant is 0 in this case. So what does it mean? So if the determinant is 0, what does it say? What does it say about the vectors? It means that these 3 vectors, 3 column vectors, do not form a 3-dimensional parallelogram. You're getting something which is flat. That's what that means. So what we're saying is, if you look at these three vectors, so if you write these vectors out, so x1 is the first column vector, 1, 4, 7. And then x2 is the second column vector, which is 2, 5, 8. And then x3 is the third column vector, which is 3, 6, 9. So that's what we're saying. You see, we're saying that we have these three vectors over here. These three vectors, if we were to draw these three vectors in space, we will see that one of the vectors falls inside the two-dimensional plane, the two-dimensional parallelogram, which is determined by the first two. So in other words, you are not getting a 3D picture. That's what that means. So, like, if that's not clear, what we're saying is this. You have your three vectors. So let's say this is x1. Okay, this is x1. And then you have your x2. So maybe your x2 looks something like this. This is your x2. And x1 and x2 together, they determine some kind of parallelogram, a two-dimensional parallelogram. Now, usually when you have a third vector, it's like pointing out. And that way you're able to create a three-dimensional parallelogram. But in this case, what's happening is the x3, it's already sitting inside the parallelogram, which is formed by the first two vectors. So you're getting something which is flat. This is a flat parallelogram. So its volume is equal to 0, right? That's what you would say. The volume is equal to 0. That's what you're saying. So if you were to carefully draw these pictures in space, which is not easy to do. It's not easy to graph pictures in space. But if you had some kind of software, maybe some of you have software that allows you to actually graph vectors in space and then rotate the pictures so you get to see it. If any of you have that kind of software, you can try it for yourself. If you were to take these three vectors and you were to draw them in space, you will see that this is what you create. You're not actually creating a three-dimensional image anymore. And so because of that, it's not a surprise why the volume is 0. It has no volume. That's why this comes out to be equal to 0. So that's what you would get if you were to do that. Now let me say some more things about this. So let's write down like a general, this is called, maybe I call this the combinatorial formula for the determinant. So it says that say A is an n by n matrix, then the determinant of the matrix is equal to this. So this is the way you do it. It's a sum of terms. I'm going to put a sigma down here, and the sigma is a permutation. So it's a sum over permutations. And the way you do it is you choose some position in the first column. This is the first column. You have to multiply it by some position in the second column. And you multiply it through by the nth position you choose in the last column. But then you have a plus or minus sign. And the way you write this is you just write the sign, SGN, of the permutation. And a permutation is simply a reordering of the numbers from 1 to n. And that's really what you're doing. So like, for example, So for example, if you have 4 numbers, 1, 2, 3, 4, then here are some examples of permutations. You have to reorder this. Like you can write, for example, 2, 3, 1, 4. That's one order. Another type of order you can have is 3, 4, 2, 1. That's another way you can write it. Okay, and you have others. So sigma is a permutation. Sigma represents this entire, that's one possible permutation. So if let's suppose you're using 2, 3, 1, 4, and sigma represents this entire permutation like this, in that particular order, then sigma of 1 just means it's the first number in the list. Sigma of 2 just means it's the second number in the list. That's what it means. So what you're doing is you are choosing, you see, in the first column, you are choosing some permutation. This is the first position in the permutation. Then you're choosing the second position in the permutation, choosing the third position, and so on. And then you have to determine the sign of the permutation. And the way you determine the sign of the permutation is by determining how many flips you're doing. So in this particular case, because you have 2, 3, 1, 4, if you flip 1 and 2, then you get 1, 3, 2, 4. And now if you flip these two, you get 1, 2, 3, 4. So the sign here would be +1. So that's the way you write this formula out in general. So that's the way this formula would look in general. So in general, the way you find the determinant of the matrix is you're multiplying, you have to choose a permutation. So you have to take the numbers from 1 to n, and you have to reorder them in some kind of a way. And then after you choose a particular permutation, that is telling you how you choose the row positions in each column. And then you multiply them together, and then the sign tells you whether or not you've chosen a positive signed permutation or a negative signed permutation. So that's the way, this is the general formula. And I call this the combinatorial formula because the word combinatorics comes from, it comes from the word combinatorics. Combinatorics means it's the looking at all possible combinations that you can take to multiply out the numbers. Now, the problem with this formula is, in general, there's too many combinations. That's the issue. So this method of calculating the determinant works well for some matrices. In general, it is very tedious to use because the determinant of the matrix will, in general, consist of 100 factorial terms, because that's how many permutations you have. So I'm going to quickly remind you what a factorial is. So think of it like this. If you have numbers, so if you have numbers from 1 to 4, how many different ways can you reorder it? So you will notice that you have 4 choices to put in here. So there's four choices, right? You can pick any one of the 4 numbers. But after you pick a number, let's suppose you say I decide to use the number 3, then into the second position you only now have 3 choices, because you're not going to be using the number again. You have to use something else. You're avoiding repetition. So maybe you end up using 1. You have 3 choices here. So you end up eliminating that one. And now in the next position, you have 2 choices left. You have 2 choices left over of what you want to put there. You can either use 2 or 4. Maybe you decide to use 4. Okay, and then you're forced to use 2. So that will give you one possible permutation, 3, 1, 4, 2. And in the last position, you only have one choice. So the total number of choices, it's the product of these numbers. So in total, you have 4 times 3 times 2 times 1 choices, which in this case is 24. There's 24 choices. And the mathematical way of writing it, I'm sure you've seen this before, is you write 4 factorial. 4 factorial means you just multiply numbers down starting at 4. Okay, that's what that would mean. So I meant to say this, like going back over, if you're wondering why am I writing 100, I meant to say n factorial, but what I wanted to say is, so a matrix which is 100 by 100 will contain a matrix which is 100 by 100. If you calculate its determinant by this method, you will need to use 100 factorial terms, which is a really big number. Okay, let's not even say how big that number is. That's a really big number. If you want to see how big that number is, I mean, you can just, fortunately, Mathematica can do that for us in just a second. You just want to see how big that number is, okay? That's 100 factorial. There it is, 100 factorial. That's how many terms the determinant will consist of if you try to expand a 100 by 100 matrix using that approach above, by writing out every single combination. Now, I'm pretty sure that is more than the number of particles in the universe. And since the computer has to store memory on something physical, you do not have enough particles in the universe to even keep track of all of the combinations that are involved. However, if you input a 100 and 100 matrix into a calculator, it can probably find for you the answer to that within a second or even less. And if you're wondering what it's doing, it's not actually doing it that way. There are different methods you can use to find determinants in faster ways. You're not actually required to multiply all of those numbers out. We're going to be actually discussing some methods that make calculating determinants easier. But let me say this. This is what I wanted to say here is, so in general, this combinatorial method for calculating determinants is ineffective because for large matrices, the total number of combinations of the numbers you need to multiply is too big. There are other methods for doing this faster. And we'll discuss that. We'll actually say something about this on Thursday. However, if the matrix is sparse, which just means it has a lot of zeros, then it is easy to use this combinatorial method. So let me give you an example of what I'm saying. So here's a 5 by 5. So here's a 5 by 5 matrix. So let's look at this. 1, 2, 3, 4, 5. That's the first row. The second row is going to be 6, 7, 8, 9. And let's make this a 0. And then is going to be 10, 11, 12, 0, 0. And there's going to be 13, 14, 15, no, 0, 0, 0. Then we're going to have 15, 0, 0, 0, 0. And then we're going to write 16, 0. Actually, no, that's it. There's nothing else. Let's just check. This is a 5 by 5 matrix. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So if you try to multiply, if you try to look at every single possible combination of multiplying these numbers out without repetition in the columns, then there's 120 such possibilities. But you do not have to actually look at all of them, because anytime you hit a 0, you know that multiplying by a 0 gives you 0. So that makes things a lot simpler. Okay, so like for example, you're not going to pick a 1. If you choose a 1, for instance, if you choose a 1, you're not going to choose any numbers in that row because you have to avoid the repetition. Now let's look at this column. Let's look at the last column. In the last column, you have 4 numbers to choose from, but they're all 0. And multiplying by any of them will just give you 0. So what you do is, I'm going to go from right to left. It'll be easier if you think of it from right to left. If you go from right to left, you have to pick a 5 because all of these numbers are zeros. But now look at this second column. In the second column, you cannot pick a 4 because that's occupying the same row as the 5. So you're forced to pick a 9. You cannot pick anything else because even though you do have 3 other numbers to choose from, they're all 0. So there's no need to multiply them by them. Now, you pick the 5, you pick the 9. Look at the third row. In the third row, you cannot pick the 3 and the 8 because then you're just repeating the basis vectors. So you're forced to pick a 12. You have to pick the non-zero numbers. So you're forced to pick a 12. And now if you pick 5, 9, and 12, you've chosen the first 3 numbers over here. You cannot choose, choosing a 0 is unnecessary. So now you're therefore forced to pick 14. And now you're forced to pick 15. And that is the only non-zero multiplication that you get when you do this. So what you get is, you get that the determinant of this matrix is actually very easy to find because there's only one combination that works, and it's the product of those 5 numbers. And then it's a plus or minus sign. And the way you determine the plus or minus sign is, let's write down the permutation that we used. We did 5, 4, 3, 2, 1. If you look at it from left to right, we've chosen the 5th number in the first vector. In the second vector, we've chosen the 4th number. In the third vector, we've chosen the 3rd number. In the 4th vector, we've chosen the 2nd number, and then we've chosen the 1st number. And now you just have to rewrite this in the correct order. So in the correct order is, if you flip the 1 and the 5, you get 1, 4, 3, 2, 5. Now if you flip the 1 and the 4, you get 1, 2, 3, 4, 5. Okay? So you flip the 5 and the 1, so that's 1, 4, 3, 2, 1, 4, 3, 2, 5. And now here what we're doing is we're flipping the 2 and the 4. And you flip the 2 and the 4, you get 1, 2, 3, 4, 5. So the correct sign is therefore positive. This is positive 1. That would be the correct sign. So that would be the determinant of this matrix if you do it. Now, in the last 10 minutes, let me give you a deeper interpretation of what the determinant represents. So here's a deeper interpretation of the determinant. So we can think of matrices as linear maps. And the determinant tells us the spatial distortion factor and whether the linear map is orientation preserving or reversing. Okay, so let's, like, for example, let's look at this example. If you look at this matrix, cosine theta minus sine theta, sine theta, cosine theta, if you recall what this was, this matrix acts as a linear map by rotating vectors by an angle of theta. Call this matrix A. Now let's calculate the determinant of that matrix. If you calculate the determinant of this matrix, you would get that it's cosine theta minus sine theta multiplied by minus sine theta. So that gives us cosine squared theta plus sine squared theta. And look at that. That's the only identity that we remember from trigonometry. So we are so lucky, and we know it's equal to 1. Now, what's the significance of 1? Because the determinant is positive, it means this linear map is orientation preserving. And because the determinant is equal to plus 1, it means there is no spatial distortion factor. So for example, if you look at a before and after image and you apply to it this linear map, so this is the before and this is the after. If you have a before and after image, like for example, let's suppose you have some kind of triangle like this. This is the before image. And then you apply this matrix to that image. What's going to happen with that triangle? Well, that triangle is going to rotate. That triangle is going to rotate. This is, I mean, because A is a rotation, you're rotating the triangle. This triangle is going to rotate. But because the triangle is rotating, so because the triangle rotates, it means it is orientation preserving. Right? Rotations do not flip your orientation. Things that are on the left and on the right stay on the left and on the right after you rotate them. And the triangle does not get any bigger. It's just a rotation. It does not get any bigger. The size of the triangle remains the same. Yes, Eric?
But there's like a reflection over the x-axis that doesn't preserve orientation, right? Because it's like,
right. That's a good point. The reflections do not preserve orientation. So let's see what happens over here. Let's look at this example. So recall that reflection through the line y is equal to x is represented by the matrix, and we saw this before. The matrix that represents that linear mapping is the matrix 0, 0, 1, 1. And the determinant here is equal to, and this is the important point, the determinant here is -1. If you calculate the determinant of this matrix, you get -1 because you have a reflection, and reflections, they flip orientation. So that's why the determinant comes out to be a negative number. You're flipping, since the orientation gets flipped, that's why you're getting a negative number. But the reason why it's still 1, so in absolute value though, however, in absolute value, the determinant is still equal to 1 because reflections, though they change the orientation, they do not expand the size of the image, right? I mean, if you have a triangle, like if you take this triangle and you were to reflect it through the line y is equal to x, well, what's going to happen? I mean, things that were on the left become on the right, so things get flipped the other way around. But the size of the triangle does not change. It's just as big as it was before. The triangle is just as big as it was before. So that's the reason why the determinant is 1. Now, this was a question on your homework, if you recall. So on the homework, you had a problem to investigate the linear map given by the matrix. So you probably remember this homework problem. You had this homework problem where you had to look at the matrix that was given by this. I think that was the matrix. And what happened is that if you have the unit cube, if you have the unit square, so that's the before, that was the before image. And the after image, this is the after image. So if you did that particular exercise, you probably recall this is what happens. You probably end up with something like this. Maybe you remember doing that exercise. So the square that you had before, it turned into something like this. It got a little bit bigger. And if you calculated the lengths of the sides, they're equal to square root of 2. So originally, you had the unit square, but now you have this diamond shape. So you can see what happened. The effect was the square got expanded a little bit. It grew in size. So you had some kind of spatial distortion taking place. The linear map had a spatial distortion. It expanded the size of space. But it also rotated the square a little bit by an angle of, it appears to be by an angle of 45 degrees. So here we can see this linear map is you can say it's an expanding rotation. It's like a rotation that is growing in size. So the determinant, and by looking at the determinant, if you look at the determinant, here the determinant is equal to 2. If you calculate the determinant, this minus that will give you 2. So the determinant is equal to 2. So the determinant is positive, so the linear map is orientation preserving, and the determinant is equal to 2. So the expansion factor is twice as big. So the image becomes twice as big as it was before. You can see that. The area of this square was 1 unit. That was the area of the square. It was 1 by 1. But now you're getting the square root of 2 by square root of 2. The area is now equal to 2. So the area was 1, but now the area is 2. So that means that the square, it expanded by a factor of 2 in the before and after image. And that's the reason why the determinant is equal to, it's not a coincidence why the determinant comes out to be equal to 2. It tells you the spatial distortion factor. This is like the deeper explanation for what the determinant says. And the reason why this works, by the way, let me just have 1 more minute to finish this. So the reason why this works, if you're wondering, let me just go back over here. If you're wondering, why is this true? Why is this true? Well, it has to do with this. I think it would be best if I just give you a specific example. Like, let's suppose your matrix is A, B, C, D, E, F, G, H, I, like this. Let's see what happens if you apply this matrix. So say the before picture consists of the vectors E1, E2, and E3. The after image, the after picture, will now consist of the vectors. So you have to apply this matrix. So let's suppose the matrix, this is our matrix. So you have to apply the matrix to these vectors. So in this case, you would have AE1, AE2, and AE3. But look what happens if you work this out. If you do A, which is A, B, C, D, E, F, G, H, I, and you apply it to the first basis vector, look at what you're going to get if you do that. So this is 1, 0, 0. If you do the multiplication, you just get the first column of the matrix. Okay? And likewise, the same thing happens with these ones. So what we're saying is that this over here, this is really the first column of the matrix. This is the second column of the matrix. And this is the third column of the matrix. And how do you find the determinant of the matrix? You find the determinant of the matrix by taking the oriented volume of its columns. And that's how you find its oriented volume. So, but the determinant of the matrix is telling you the after image to the unit cube. You had the unit cube in the beginning, and after you apply the linear mapping, these basis vectors, they get mapped precisely into the columns of the matrix. And so by calculating the oriented volume of the columns of the matrix, you're getting not only whether the orientation was preserved or reversed, but you're also calculating the distortion factor that you're getting from the linear mapping.